So at this point, we've talked about continuity of polynomials, rational functions. We got into a little bit of piecewise functions when we talked about continuity on intervals and root functions, but that still leaves us with a whole mess of other functions here, and we're going to try and close that gap in this video. This handy theorem tells us that the following functions are continuous at all points of their domain. So first of all trig functions. So here we might be talking about, say, sine of x, cosine of x, tangent of x, as well as their reciprocals, cosecant x, secant x, and cotangent of x. It also includes all inverse trig functions. So there's a few different ways that you can write those. I think our textbook uses sine inverse of x, and then that applies to all of them, cosine inverse of x, and so on. You may also see sine inverse of x, for example, written as arcsine of x, or cosine inverse of x written as arc cosine of x, and that just depends on your preferred notation. I don't really have a preference. I'll probably stick to what our textbook uses, where sine inverse and tangent inverse and things like that. All exponential functions, so all functions that look like b to the x, and in particular e to the x is kind of the one that we care the most about, as well as all logarithmic functions, log base b of x and natural log of x. Again, natural log of x is probably the one we're going to care about 99% of our time. And the one thing I will point out here is this really important part. It says of their domains. They're continuous on their domains, which means they are not necessarily continuous everywhere. So for example, let me erase some of this here. For example, if I was to talk about natural log of x, right, let's just take natural log of x for an example. Y equals natural log of x. It would not make sense for me to say, well, this is continuous on negative infinity to positive infinity, because natural log of x, if you were to look at the domain of this function, the domain of natural log of x is 0 to positive infinity. So saying negative infinity to positive infinity doesn't make any sense. But what we can say then is, because we know its domain is 0 to positive infinity, we can then say, well, this is continuous on that whole domain 0 to positive infinity, and there's no extra work that we need to show here. So this does not necessarily say that these functions are continuous everywhere. It does say, however, that they are continuous at all points of their domain. So it's a very subtle difference, but it's a very important difference. And what this allows us to do is it allows us to evaluate a whole bunch of other limits. Because when it comes to continuity, what it means to be continuous, remember the three things we talked about for continuity. We said, okay, f of a needs to exist, the limit as x approaches a of f of x, that needs to exist, and then for the third part, we need the limit as x approaches a of f of x. We need these two things to be equal, essentially, is equal to f of a. So it's really this third property that's so important and why we care about this theorem so much, because when it comes to this example here, so now we want to look at the limit as x approaches 4 of e to the square root of x power. Here I can just say, well, this is a limit. This is the same as saying e to the square root of 4. I can just take that number and plug it in, since 4 would be included in the domain of this function. And then from here I would just simplify this. Square root of 4 is, of course, 2, e squared. And if you wanted to get a decimal, that's fine. I would just leave this as e squared, though. Limit as x approaches pi of cosine of x here. Same exact idea here. So I look at this, I say, okay, well, this is continuous on this domain. If I use this third property over here, I can just take pi and plug that in, since that's part of the domain of cosine of x. So cosine of pi in this case, I would just evaluate cosine of pi, which should be -1. So there's my limit. So this is really, really nice because this allows us to evaluate limits of a bunch of other functions that we hadn't been able to work with. Up until this point, we had barely been able to work with sine and cosine, and we'd really only been looking at limits at 0 for those. Now we can expand those to talk about all of these other trig functions. So let me throw one more in here, just a bonus example. If I wanted to talk about, say, limits as x approaches pi over 4 of tangent of x again. So before we wouldn't have been able to work with tangent of x. Now again, I can lean on this third property over here and I can say, you know what, pi over 4, that is in the domain of tangent of x, which means I can evaluate this limit by just taking pi over 4 and plugging that in for tangent. So tangent of pi over 4, you would say then is 1. That is what our limit is equal to then. So we have one more video here, one big named theorem that we're going to talk about in the next video. It's relatively intuitive, but it is an important one. So take a look at that once you feel you're pretty good with these examples.